Hey everyone, we are looking at springs today. And for a spring, it turns out there are both forces associated with them, and if there's a force and it is able to do work, there is a type of energy. While we could have looked at the forces, the spring force or the elastic force, when we were studying the second law, we put it off till now. All right, we're really going to focus on them as we apply them towards the energy of things, and particularly, of course, the conservation of energy. So we'll look at springs, look at the force associated with them, and then the energy. If you've never seen a spring before, I have a couple pictures here. Usually it's a material, often metal, but not always, and it's coiled. And the material and the coiling, the shape, is such that if you were to press down on the spring and release it, it would spring back up. If you stretched it upwards, it would return back to that initial relaxed state. So these can apply a force on an object. Right? You can push on the spring, and the spring can push on you. So let's look at that spring force, and it's often called Hooke's law, which we'll get to. I have a wall right here, and imagine I just took this spring, placed it horizontally, and I glued one end to the wall. This is my attempt at drawing a spring. When the spring is relaxed, when no one is pushing on it or stretching it, it has a certain relaxed length. We mark that relaxed length as its equilibrium position. When there's nothing pushing or stretching, we'll label that spot the spot where it's in equilibrium. All right? So here's state one. I just attached it to the wall. Let's say for part two, same spring, but now I'm stretching it. I'm applying a force to the right. All right, I'm applying a force like this on that spring. It's obviously going to stretch. Well, when that spring is stretching, it is no longer at that equilibrium point. It is some distance, which I'm going to call delta x. More than that equilibrium, that equilibrium point, excuse me. My little number 3 popped up. We'll get to that in a second. So that equilibrium position, same as where it was before, but if I'm stretching the spring, however far I stretched it, I'm going to call delta x, measured from that equilibrium position. Likewise, if instead of stretching the spring, I compressed it, so maybe I applied a force this way, I'm pushing on that spring. Well, the equilibrium position was here, whatever this distance is, whatever it was over here. Now that spring is some distance shorter, some delta x, again measured relative to that equilibrium spot. So this delta x is valuable. It's telling us how much that spring is either being stretched or how much it's being compressed. And so if you know this delta x, it's telling you what the displacement of the spring is from its equilibrium position. Okay, that spot that we're calling equilibrium. That's going to be important. We're going to use something known as an ideal spring in this class. In real life, springs aren't perfect. They're not made perfectly. There are defects with the shape, with the material. Even if the density changes slightly, a spring is a complex thing to really study and know in real life. So, like a lot of what we do, we'll make certain ideals, certain assumptions just to simplify things and make it easy. We're always going to use ideal springs, unless a problem says otherwise. And for an ideal spring, comically, it says it's one that has no mass. And that just means you don't have to worry about like the inertia of the spring or any type of resistance that the matter in a spring might otherwise apply. So don't worry about its mass. You don't have to add it into anything. And like I said, no imperfections, no irregularities. If a spring is ideal, which is what we'll mostly be assuming, it follows something known as Hooke's law. And Hooke's law says there is a relationship between the amount of force that spring is applying and the displacement of the spring, how much it is being stretched or how much it is being compressed. And the equation looks like this. The force that the spring is applying on an object, spring on object, This is the force the spring itself is pushing on an object. It's equal to two things. It's equal to K, and it's equal to delta X. Relatively simple equation. This delta X, well, that's that displacement. We already talked about it. Displacement from the equilibrium. K, that should be a lowercase k, to be perfectly honest. If I erase that, I should make it look more lowercasey. Well, whatever. This K is known as the spring constant. Spring constant. Sometimes it's called the spring stiffness. Spring stiffness. It's how stiff the spring is. If there's a large K value, and it would just depend on the spring, all right, it would have a large number. The shocks in your car, these are giant springs. They have to support the car. They have spring constants in the thousands. Little tiny springs might have constants that are like 1 or 2 or 3. The units for this are going to be Newton meters, newtons divided by meters, because I have to have newtons over here, and delta X is meters. So the unit for spring constant is always newtons over meters. This will be given to you, or you'd be asked to solve for it. All right? This equation, this is what's known as Hooke's law. Again, it's for an ideal spring. Okay? It's a linear relationship. If delta X doubles, the force doubles. If X is cut by 1/4, the force is 1/4. That's Hooke's law. All right, well, now let's take that and look at the energy associated with it. I have here a couple diagrams. All right, we know that if we take a look at the work done by any particular force, so let's look at the work done by a spring force. That's going to be equal to the force, in this case, the force from the spring, times the displacement. Well, the force is that K times X, and the displacement is my delta X. The work done by a spring eventually takes the form of this, 1/2 kx squared minus 1/2 kx naught squared. Okay, now to be honest, where we get this 1/2 and the square, I'm not going to get into. It's actually from a calculus derivation. Okay, it's not as simple as when we were looking at the gravitational force and the gravitational potential energy. So you'll never have to know the derivation. It looks like this. All right, but once again, we have these two terms, very similar, before, or I should say after, versus before, a change. Just like we've seen, this term is given a special name. It's known as the elastic energy, in more particular, an elastic potential energy. And we always use U for potential, and for a spring, it's U sub S. So US is equal to 1/2 the spring constant times X squared, where X is how far away that spring was stretched, or how far away that spring was compressed. Okay, so here's a couple diagrams. I'm actually going to pop open a little window here, and we can see a block attached to a spring that is oscillating. There's no friction over here. So it's just gliding back and forth. I'm not sure why my highlighter doesn't work on this thing, but it's moving back and forth, back and forth. Notice, the position and the force are always in opposite directions. When it's moving this way, the force is that way. Moving this way, the force is that way. Okay? The position and the force are always opposites. That lends itself to revisiting this equation here. We will often see Hooke's law with a minus sign in front of it. This is just to indicate that that force is opposite of delta X. On the equation sheet, they put absolute values so you don't have to worry about it, but not a big deal. There's this minus sign here, okay? It's just representing that the force and the displacement are in opposite directions. Okay, again, here I'm seeing it with this visual. When the spring is being displaced to the left, the force is to the right. So it's slowing down, speeding up, slowing down, speeding up, etc. Now, this energy from the force could either be conservative or non-conservative. And it turns out that the force from a spring is a conservative force. And that's what this picture is hopefully going to allow us to see. Here, the block is moving this way. So its delta x is this way. But this was its equilibrium spot. So the force is going to be acting this way. So if the object is moving to the right and the force is pushing in on it to the left, the work done would be negative. But look over here. The force is still pushing this way. But now the block is moving in the opposite direction, to the left. Positive and positive, now the work is positive. They're in the same direction. So the spring force is a conservative force. To be honest, that's where this term potential comes from. Potential is always used for conservative forces, or the work done by conservative forces. Anyway, last thing, then I'm all done. We have one more thing to add to our conservation of energy. Now, not only do we have kinetic energy of objects and gravitational potential energy of objects, we also have the spring energy of objects. Here's an object. Here I have a rock. Maybe it starts at rest. It's released. It's falling. It's moving. It hits a spring. It compresses the spring. And then what do you know? That spring then decompresses. It pushes upwards, and it launches the rock back into the air. There are three different energies going on. So to apply conservation of energy, remember, E is equal to E naught. Or I should say E naught is equal to E. An object might have some kinetic energy, might have gravitational potential energy, and it might have spring energy. Whoops, that should be an S. That could be final energy plus final kinetic energy plus final gravitational plus final spring. We could have an enormous, a terrifying looking equation, x naught squared equals 1/2 mv squared plus mgh, oh no, plus 1/2 kx squared. Ugh. Luckily, you'll pretty much never see something this big. You'll have things drop out. For example, on this problem, it starts off with no motion, so right away, this would go away. And there's no spring up there, so that would go away. If we were comparing it when it got right down here, then maybe there's no more velocity if it's at rest at this spot. All right, maybe there's no more height if we're taking height as this measurement here. Anyway, get the idea. One more type of energy we could include in our conservation of energy equation. All right, I'm already way over my time. I'm going to stop there. We'll talk about these springs a little bit, and then we'll start applying it to our problems involving conservation of energy and some including forces, because now we know the force too. Thanks for watching.